Hello, everybody. Thanks for joining me on an early afternoon on the last day here. My last day, at least. My name's Chris. I'm going to be talking today about data center network design for the media and entertainment industry. Now, depending on who you are, you might have experience in media and entertainment, you might not. This might be a new thing for you, but we'll get to what that means in a few minutes. If you have any questions after the session, you can post them in the WebEx app for the session. I'll answer that as fast as possible. Do note that I live in Canada, so time zones might be a bit offset. But today, we're going to talk about broadcast. Reimagining what broadcast workflows are. We're going to talk about live production fabrics and IP fabrics for broadcast, contribution and distribution fabrics, synchronization of all of this, how we can get visibility into that. We're going to talk about broadcast master control, broadcast playout, and graphics. And then we'll conclude with a summary. But first, a little bit about me. I come from the broadcast industry. I've worked in it for almost 16 years, 16 years and a few days, actually. I've worked in broadcast IP and IT for about 10 years of that. And I've been a Cisco TSA for coming up to the 4-year mark. We're going to use Slido today, so if you could please join the Slido at this QR code. Any questions that you have during the session, you can post them in the Q&A on Slido, and I'm also going to ask you a couple questions with the Slido as well. Just wait for me to stop seeing phones in the air, and then I'll go on. Alrighty. So as promised, a question. What does networking for media and entertainment mean to you? $2110. And if you don't know what that is, don't worry, you will. Mass content, bandwidth, multicast, bandwidth. This is the first time, I think, that I've asked this question and actually had this many people put in 2110, Dante, AS67. A lot of you guys must know what those are. That's good. PTP. Well, I think you could probably guess that one of the very big topics that we're going to talk about today is obviously multicast. So a lot of you seem to know that answer. So we'll go on here. So again, we're going to talk about reimagining broadcast workflows. So in broadcast, we have production, we have editing, we have playout, we have graphics, contribution, master control, distribution. For those of you that don't know what that means, production is when you make the content in a studio or at a sports stadium, something that you're filming live. Editing, you put together packages, you put together specialty content. Playout could be playout of an event using a server that was pre-recorded. It could be playout of a commercial. Contribution is when you pull feeds into your facility. Master control is when you do things like adding in ad insertion, the commercials, like lower third graphics, news tickers, weather alerts. Distribution is when you send that signal out of the building in some way, shape, or form. So why is IP technology important for broadcast? Well, for those of you who know me, I'm only 34 years old, and I've worked in broadcast for a long time, and I've seen a very large transition just in my short time working in this industry, and the people that came before me saw even larger transitions, going from analog to digital, to standard def, to high def, to 4K, 3G, dual link SDI, all these different things. The industry is constantly evolving, and that's generally driven by the consumers wanting to get better content, faster, higher quality everywhere. But a bit of a recap as to how this all works is inside of a broadcast facility, there is a video router and there's an audio router. Back in the day, they were two separate things. Sometimes they still are. We had the contribution side, and we typically use things like satellite and microwave. Usually at a sports stadium or at a mobile truck or at a news van, we had encoders, and they could send that to the satellite or put it across a microwave link. We had something called an IRD, or a receiver, in the broadcast facility, and we'd get that signal, we'd send it to the video and audio router. If you don't know what microwave is, it means you actually have to see where you're sending the signal to, so we had to put those really high in the air, and satellites are very slow. Then the whole service provider world started, and we started to use dark fiber. We'd still technically sent it as a video signal in the early days across that dark fiber. Then cellular came. The first company I knew about that used cellular was in Canada and Waterloo, and they basically found a way to take 3G cellular, bond multiple SIM cards together, and be able to send an uncompressed broadcast feed over top that, which was really cool back in the day. You no longer needed to get this big truck and put a mast up in the air, pointed at the CN Tower in Toronto, and then hope that the signal got to your facility. You could just send it over 3G. So we used that. It's the public internet. Then we started using public cloud to send signals, but all these things started to use IP. So we really benefited from that IP, but we still, at the end of the day, put it into a receiver and then sent it into a video and audio router. So we used IP for a long time, but still sent it what we call baseband. Then it went into master control, and then it made it out to the consumers. But what if we just used a broadcast facility built on IP? We no longer have to have a separate video and audio router. Sometimes we don't even need that IRD. If we can ingest the content natively as some kind of multicast or even unicast that we understand, MPEG, H.264, H.265, 2110, we can bring those right into the network. So let's talk about contribution, bringing in sources from external parties, production, whether it be in studio, REMI production, remote production, distributed production, master control, to air playout and ad insertion into our TV stations, pre-recorded content and branding, and distribution. We typically would have a separate router to handle all these entities inside of a facility, unless you were a small facility. But in the facility I worked at, we had 89 master controls. And every single master control had its own router, both for audio and video. Kind of senseless. We can connect all these now with IP. If you're not familiar with the JTNM is an entity that we participate in. It's called the Joint Task Force on Networked Media. So the JTNM defines that in the world of broadcast and in the world of media, there exists 3 logical networks. They call it the amber network and the blue network. I call it red and blue. Doesn't matter what colors. You could even call it gray and darker gray if you're colorblind. And there's also a control network. Logically, these are 3 separate networks. Physically, they could be. It could be the same network. They could be somehow physically isolated just from control. You could only have isolation in the media networks. But logically, you need to have 3 or at least 2 if you're not redundant. What we're talking about today focuses on these 2 networks. How to do this part really, really well without dropping a single packet. Because in broadcast, 1 packet is millions of dollars. Could you imagine, for those of you who watch football, American football, could you imagine if 1 packet dropped during the halftime show of the Super Bowl? Not a good thing. So, the industry challenges and requirements to do this, we can't change that operator workflow. They have to hit a button, and what they hit has to happen right away. It needs to be deterministic and low latency and have low jitter. It has to have 0 packet loss. Every video and audio endpoint needs to be in sync with each other. And it needs to be fast when we hit go to the next flow. The system availability needs to be at least better than SDI, if not better. And for the broadcast people in the room, we finally have to talk about security. Because for the longest time, security was not even a consideration in broadcast. What we did for security was just not plug things into the internet. So I'm going to give you guys a little bit of a lesson in video and some standards out there for those who don't know it. I will apologize ahead of time because it seems like I have a lot of broadcast people here. When I mention things, I'm going to talk about the North American standards like NTSC and stuff like that. I apologize. I know you guys are PAL. Inside the media world, I always say that we have standards and specifications and systems. Standards and specifications are things that are globally adopted, open standards, have interoperability, and they work very well and they're tried and true. JPEG 2000, MPEG 2, 2110, 2022. Now we have IPMX that's being created as well, and JPEG XS is very, very mature now. We need to work with all those. They all need to interoperate together. But we also have things that are systems. And systems are closed environments, things like Dante. And Dante is really great at what it does. It's plug and play, but it has a breaking point of scale. NDI, really great, but how do you stretch it to 10,000 endpoints? There's also SDVOE, there's SRT, CDI, and there's even AVB Milan. These things, we want to operate and support as many of them as we can, but sometimes it's hard because, again, they're closed systems. And a lesson in video, one of my favorite topics. What is ST2110? So I know this isn't a Slido, but put your hand up if you know what ST2110 is. All right. Not too many, but enough. So in the world of video, we had NTSC and PAL. Now, that is the actual video signal as it travels across a cable in analog, and when you pull it up in a waveform monitor, you can actually see the blanking and you can see the colors, and if you move something in front of it, you can actually see the picture in the actual wave of the video, for the most part. Well, we needed to move that to digital, and we did that over something called SDI, or Serial Digital Interface. And we actually had to maintain the amount of time. So who here remembers CRT televisions? The tubes. So when tubes draw a picture, as it gets to the side of the screen, it actually has to move the gun back to the other side. And then go and move the gun, go move the gun for all the lines of video. And then when it gets done, it has to move the gun back to the top. That's a physical process. It takes time. In analog, we call that blanking. But now that we're in digital with LCDs and things like that, we don't have blanking anymore. But we have to maintain that time because we decided in the broadcast industry that we're going to maintain backwards compatibility all the way back. So if you have a digital signal, we still need to be able to broadcast it on an analog device. So we maintained that time, and we called it the vertical blanking period and the horizontal blanking period, and then we decided that, wow, it's really cool. We can actually put data in here, just like we do in IP. Put packets in there. You are familiar with these packets. Those packets are audio in the horizontal space, so that tiny little amount of time as we're moving back and forth from line to line, because it happens so fast, we can put the audio packets in there and have uninterrupted audio. And then in the vertical space, which is where we go from the bottom to the top, we can put things like closed captioning, things that are slower. So we started packetizing data way back even on an electrical cable. And then we decided that we needed to send this over IP. And our first attempt at it was not that great, but it was good enough for what we needed it for. So we took that entire SDI and just encapsulated it right into a 1428 byte IP packet, straight across the line. Not very flexible. In broadcast, we like to mix different audios, mix different videos, put them all together and make something new. You can't really do that when everything's just crammed into one. But we called that 2022-6. And now ST2110. So instead of doing that, we decided that we were going to do something called essence-based media. And what that means is we're going to take these different entities, like the video, the data, the audio, and we're going to split them out into different IP packets. Ancillary data in 40, video in 20, audio in 30. Now the reason I'm telling you this is because these three things, and all the other ones that have come since, have very different disparate bandwidth values. So ancillary data, it's kilobits a second. It's not that much. Audio, somewhere between 10 megs and 250 megs. For 1080p video, not that big, but 1080p, almost 3 gigabits a second per video stream. Probably around, in the European realm, probably around 2.4 gigabits a second. In America, we're at about 2.6 because we have some extra frames. And that's for every single video signal. And a broadcast facility has thousands of video signals. 4K, almost 12 gigabits a second per video stream. Very disparate from its kilobit per second data counterpart. 8K, about 50 gigs per video stream. But we're not really worried about that yet. There's only one person in the world doing bandwidth that big. And if you're like me, you really, really like to read RFCs, and so I'll tell you how we got here to 2110, very quickly. We have RFC 3550, which is RTP. And we decided that that's not good enough, so we went up to RFC 4175. Does anyone know? You can just raise your hand if you know what 4175 is. It's the carriage of uncompressed video over RTP. So it's kind of an addition to that, but it's specific to uncompressed video, which is what we need in the broadcast industry. And in the audio world, there's the Audio Engineering Society, and they were creating something called AES 67, which is how you send audio, professional uncompressed audio over IP. And the industry decided, when a guy from Fox Television got everyone together in a room from all the different vendors and said, you guys need to start working together, otherwise we're not going to buy your stuff. And so he created something called the VSF, the Video Services Forum, with a few of his friends. And they created this thing called TRO3, Technical Recommendation 03. And that was how they wanted the industry to adopt an open standards-based media set of protocols. And from that, something called SMPTE, SMPTE, Society of Motion Picture and Television Engineers, created SMPTE ST 2110. 2110 is a collection of standards. So as I showed you before, we have dash 10, 20, 30, 40. There's now 41, 42, 22, 23, 33, many, many of them. But we had to create these different subsets. So 10 is timing and system, 20 is video, 30 is audio, 40 is data. We created a few more based on that, as I said, 21, 22, 23, 31, which is the Dolby carriage audio, PCM. We have 41 and 42, which are for fast metadata, things like HDR, to be able to dynamically send it across the network. You don't have to remember any of this. Just remember it's a lot of bandwidth. But if you're interested in reading standards, these are all the ones you need to know. Oop. Okay. So I'm going to stop for questions every once in a while. So we have two questions here. What is the better open source software to play with NMOS SDP files? So I haven't gotten to what SDP files are yet, but I'll answer this question. There is an open source NMOS repository that the industry has basically adopted. It was originally started by Sony. It's called NMOS CPP, and you can develop your own and start up your own NMOS registry with that one. Is it possible to use a local PTP GM clock? We'll get to synchronization later, so let's save that question for later. Don't let me forget about it. I'm just going to see if there's any other questions here. No other ones yet. All right. Clicker is being a little delayed. So I promise you that that is the most we'll talk about actual video in the whole session, and now let's start to get to the network. But I think it's important that everyone understands that, like, all the different cool elements of broadcast before you start building a network for those things. But how do we do the actual network for all of this traffic that we just talked about? First, we're going to focus on the production side of things. In studio or REMI, doesn't matter. In that production, we have endpoints, things like cameras and audio endpoints. We still use big glass cameras generally in a lot of broadcast environments. They could be smaller these days. We have video servers, video switches, multi-viewers, and audio mixers. I'm sure that a lot of people here have seen Star Wars. You know, when they go take the Death Star and they do that little thing to turn it on, that's actually a video production switcher that was just repurposed to do that scene. Producing or consuming signals in live production, we do that as well. We bring signals in from sports venues, from news hits. These are the things that we all need to integrate together. And we might have some legacy devices or devices that just haven't adopted IP yet, so we need gateways for that. And in most cases, we use something called SMPTE ST 2022-7 for redundancy. So ST 2022-7 is specific about redundancy, and that means that the device has two physical interfaces in most cases, and the live video will go in both interfaces from two different other interfaces simultaneously, and the device picks on a packet-by-packet basis which one's better. So you actually send active video across both at all times. So keep that in mind when you're building these fabrics. It's not like VPC redundancy or anything like that. Full tilt, both networks, all the time. In the early days, majority of people did what we call monolithic deployments. That means everything just connects to one switch. The reason we really did this in the early days, at least in my opinion, is because when we started this, 100 gig was the fastest speed that we had. And most of my broadcast devices had 100 gig interfaces. And so because over that 100 gig interface, I'm actually sending 100 gigs, it didn't make sense to spine leaf your way down to 100 gig to 100 gig to 100 gig and just get all the way there with the same speed. So everyone just connected everything to one. But for some deployments, we did see spine leafs deployed, and today that is primarily what is deployed because we have these higher bandwidth speeds. But we also came up with the idea that you could do a hybrid. You could connect the high bandwidth ones to the spine and low bandwidth ones to leaves. And this is typically still the way most people deploy it. Some kind of fabric with some kind of spine leaf, or many multiple fabrics with some kind of spine leaf. So this is how we'll deploy these, probably going forward for a long time. We won't do a mesh network because, again, we're dealing with multicast, and in a lot of cases, multicast does not like mesh networks. And you could have that one device that's any source multicast based, and that just messes everything up. So what is an IP fabric? An IP fabric is a set of network nodes connected to endpoints. I think everyone here knows that. Based on the endpoint scale and their port requirements, we have to build a fabric. So unlike in IT, where we design a network and we connect things to it, when you design a broadcast fabric, you need to know every device that's going to connect before you build the network, before you choose the switches. Because I can assure you, you're going to use many vendors' pieces of equipment. And when I tell you that every single one of them is going to connect at a different speed, some of them use 4 by 25 gig across a QSFP, some of them use 10 gig, some of them use 50 gig, some of them use 200 gig, some of them use 100 gig. And unless you know all that, you can't choose the right switches, because remember, again, we're going to be non-blocking because we have all this bandwidth. We need to make sure that we build the network for our devices and not build the network and let people come to it. So bandwidth, talked a lot about bandwidth. The bandwidth from the leaf to each spine needs to equal the bandwidth of all senders on that leaf. So if I have 200 gigs worth of senders on my leaf, I need to have 200 gigs to both spines, because I need to maintain that source state in both spines to be perfectly non-blocking. Now, you could argue that you don't need perfectly non-blocking in some instances, but that's up to you as the end user. And then the bandwidth from the leaf to all spines aggregately should be equal to all the receivers on that leaf. Because in the perfect scenario, I can get a received flow from either spine, but I don't necessarily know how that spine is going to transit my source to other leaves. So that's kind of the math at a high level. So what that can look like, if we build this in a non-blocking class architecture, we can do it with a single spine or a dual spine. It's important to note that in my diagrams, I'm drawing one network. But if you adopted 2022-7, you'd have 2 side-by-side networks, perfectly mirrored of each other, running all the time. So the benefit of having 2 spines is that you can survive a spine failure. So if you're running non-2022-7, it might be important to you to actually deploy a 2-spine design. If you're running 2022-7, you still have that other network that's probably fine, so you can usually get away with just doing 1 spine. Those are the differences there. Most people in a big facility do 2022-7 because it provides that packet level redundancy. But a lot of the sports stadiums that we work with in the US and in Europe, they might go for more the opted single spine design or single side design and do a dual spine so that they can have at least some redundancy. There's also an important note. We need to choose how we want this system to work. And so for all the regular networking people in the world, that's what we call network-driven architecture. Our network decides how to do things for us. Switches and multicast with a network-driven architecture use PIM, and we're going to use something called NBM, which we'll talk about. The bandwidth is controlled by the network. But then in the broadcast world, we have this whole concept of an SDN, and it's not like a normal network SDN. What that means is that the broadcast SDN will take that multicast and send an API call to every single port that it has to show up on and manually stitch that multicast across the network to give it some deterministicness. They do that for bandwidth awareness, but also so that they can explicitly control what happens. But they're in charge of the bandwidth. And we'll talk a lot about bandwidth. In order to build an IP fabric, we also have some other things that we need to include. Layer 3. Please do not do layer 2 multicast at scale with 12 gigabit flows. It's not going to go very far. It works until it doesn't. We also need to make sure that we use some kind of IGP. Typically with these fabrics, we use OSPF because it's very easy to troubleshoot and it's very scalable for the size of fabrics that we're doing with this media. We need PIM for the multicast routing. So we're going to add PIM sparse mode. And then we need IGMP at the edge. So our devices typically are going to be IGMP v3. There are a few IGMP v2 things out there. But we also need to make sure that we use that immediate leave function. Again, remember, these are 12 gigabit multicast, maybe some 3 gigs. If we don't leave it immediately, if we wait for the timeout, that port is going to get oversubscribed and be over the actual bandwidth that it can receive in a lot of cases. So you need to make sure that you include immediate leave. And we need QoS. I love QoS. We need to make sure that that media traffic is delivered very fast as we can, and all of the bandwidth. But we also need to make sure things like our timing are efficiently delivered and delivered extraordinarily fast. So, multicast routing, PIM and ECMP. Raise your hand if you're familiar with PIM and ECMP. Pretty good. Not just the media guys. So, with PIM, when multiple paths exist between the source and receivers, we're going to load balance the traffic with ECMP, just like we do anything else. ECMP uses hashing to determine which path is used. But who here knew that PIM and ECMP have no idea what bandwidth is? It thinks that every single flow is completely equal and treated all the same. It doesn't work very well. Remember that we have some flows that could be 12 gigs, and we have some flows that could be kilobits a second. But to PIM and ECMP, they're exactly the same. So what could happen is when I request flows, if I route my video audio data, and then when it hit stitches across the network, it'll go video audio data across the links. Because I have 3 links, I'm requesting 3 flows. It'll probably end up something like this. And I'll do another one. It'll end up like this. Another one. It'll end up like this. Well, what just happened is I just put 3 video flows on the first link, my audio on the other, and data on the other, because I'm routing them in the same order. And the hashing is basically stitching them out like that. If I request one more, what just happened there? I oversubscribed that link. And this actually happens a lot more than you think it happens when you're dealing with high bandwidth multicast. It is a big problem. And in the early days of doing IP video, we did not have a solution for this. The whole industry never thought that this was going to be a thing, but it ended up being a very big problem. We need to find a way to do proper load balancing of multicast with PIM. All right. So I see another question. Is source-specific multicast or BIDR important in this domain? So the media standards are typically based off sparse mode. We don't see a lot of BIDR out there. BIDR really isn't required for media, but sparse mode is very important. And there is another version of PIM called PFMSD that really works really well in the WAN for multicast video. It's PIM flood mechanism source discovery. And it's the essential ability to have PIM without rendezvous points, but also support both ASM and SSM at the same time. So if you have a lot of multicast in the WAN, PFMSD might be another option as well. And again, we'll get to the PTP question. Come on. So for that bandwidth awareness, we created something called non-blocking multicast, short form NBM. NBM brings bandwidth awareness to PIM. What this does is it actually uses a flow bandwidth parameter in order to do that hashing. So instead of regular ECMP and the ECMP algorithm, we add bandwidth to a policy in the switch and tell the switch how much bandwidth that flow is worth and load balance based off that as well. This bandwidth parameter is a policy that's applied to the entire network via our controller, but also can be informed to us by what we're calling the broadcast controller. So there exists this entity at the top. Those are made by companies like Evertz, Grass Valley, Nevion, EVS. They inform us based on the NMOS discovery of those devices how much bandwidth they're worth. But what this allows us to do is prevent link oversubscription. So not only will we load balance based off this, but we'll protect the network as well. So we created 2 modes for NBM, and the first is NBM active mode. This is that network-driven architecture. This is the way that networks have worked for a long time. The broadcast controller instructs the destination to switch using something called ISO5. For the non-media people in the room, that means it tells it to do an IGMP join. The endpoint requests that path to be set up via IGMP, and the network sets up a non-blocking path from source to destination. We do that all under the hood. All it has to do is give us an IGMP join, and bandwidth-aware will route that flow across the network. But we found out that not every broadcast endpoint supports IGMP, so we developed another one inside of active mode where we can actually send an API call to that last port in order to tell it to route the flow there, just in case that endpoint can't do IGMP. Less and less of a problem these days, but the API exists. Inside of NBM active mode, we had to think about security. And so this is essentially zero trust with a different name that's more suited for the broadcast industry. So with the host policies, we have to explicitly authorize an endpoint to be able to send or receive traffic. If we do not have a policy that matches it, we will block that content. You can be as flexible as you want with these. You can have the default be anyone can do anything. You can bring it all the way down to say this endpoint can only get this one flow. So you can be as flexible as you want. A good way to think that this can also be used is at the television station I worked at. We had both adult content and children's content in the same facility. And in the electrical world, you just never connected those 2 worlds. But in the IP world, you need a way to not allow those 2 things to touch. You can use host policies to not build trust between those 2 entities. So the adult content can't accidentally show up on air during the 6 o'clock news when kids are looking to see if their buses are canceled. And the flow policies. So the flow policies are those bandwidth parameters, the QoS parameters for the flow. So we basically instruct the network that this flow is worth 3 gigabits a second, or this range of flows is worth 3 gigabits a second. And these can be as flexible as you want. You can do them in ranges, you can do them individually, you can do subsets, however you want. But what we also do with that is program something called a policer. And we all know what policers are. They're stopping things from happening. But let's just say in a broadcast world, you have a camera guy who's going and doing his show, and it's in a 1080p show, but he wants to rehearse for something he's doing next week, so he suddenly flips the camera into 4K mode, and instead of sending out 3 gigs, now it's sending out 12. If that's hashed across the network, you could break things. So what we'll do is at that first port where the flow shows up, we'll police it to say, you're not allowed to send more than that, and stop it from coming into the network and destroying anything downstream. That's an optional feature, but enabled by default. What we also do with this is help out those devices that don't necessarily understand bandwidth. Some devices have just 6 receivers inside of them, and they could receive 1080i or could receive 1080p. What that means, if it's connected to a 10 gig port, it could get 3 1080ps, maybe 6 1080is from a bandwidth perspective. But it doesn't know that. So if it requests more than that port can actually do, we will gracefully deny it and say, you're not allowed to have that because you don't have room, but we'll hold it here until you're ready for it. So that's another thing that happens automatically with NBM based on the policies. And then there's passive mode, NBM passive mode, the controller-driven architecture. So this is where those broadcast SDN controllers can send an API call to our network and stitch that flow hop by hop across the network. Duly warned, inside of this mode, we don't do anything with IGMP, we don't do anything with PIM, and all our multicast intelligence goes away and is left up to the broadcast controller. They are the ones in charge. And all interaction with us is done using the REST API. You cannot provision flows on the CLI. It's all up to that broadcast controller. So you might be asking, well, how do I build this? Who here owns a Nexus 9000 switch? Who here has at least the Essentials license? You can turn on IPFM, IP Fabric for Media. You can turn on NBM. All those features are available to you. It's supported in everything from FX, FX2, FX3, GX, GX2, H2R. For the modular chassis, if you have a 9500, it's supported on the -R and R2 variants of that chassis. It's supported on the 9400 mini chassis and the 9800. So all of those switches can support this feature set. It runs NXOS. NBM is the feature inside of there, and we can manage it with Fabric Controller or Nexus Dashboard. It's technically optional, but I think by the end of this, you'll really want it. So in media mode, Nexus Dashboard, or NDFC, can do all the bootstrapping of the switches. I think we know what Nexus Dashboard can do. So all that day zero provisioning, image policies, configuration of the switches, but it also visualizes the topology and endpoint visibility from a broadcast perspective, not just from an IT perspective, but we can look at it from a broadcast perspective. Inside of the broadcast world, we have these things that I call friendly names. When an operator goes, camera 1, go to this monitor, destination 10, we can actually publish those names into Nexus Dashboard automatically so that you can see camera 1 and camera 10 on your topology view and see the multicast going across. We can also manage the host and flow policies instead of you having to go to the CLI. There's an API gateway for those broadcast controllers to talk to us, and we can do all the health monitoring. So that's what ND provides for IPFM. So, big question, who likes to use the show IPM route? If you like to type in show IPM route across, let's just say 20 switches to find out where your multicast is going. I do too, but I don't like to do it very often. It's painful, right? Show IPM route, ingress interface, egress interface. Okay, other side, show IPM route. Which ingress interface, which egress interface? Is the flow actually active, or is it just sitting there non-active? Trying to figure all that out can be painful sometimes, especially when millions of dollars are on the line during a live broadcast. Probably not the time you want to be doing that. All right. So all of the data that I talked about with NBM, with the active mode, if the graceful failure happens, if somebody fails to make a route, if anything happens in the NBM layer, we stream that data back to Nexus Dashboard so that it can have that real-time state, the streaming telemetry about that process. And so what this means is we can build out topologies and we can look at this. So this is an actual fabric running in the US. And this is just the video portion of the fabric. The audio portion is another fabric. And this is a 3-tier spine leaf. I can tell you that this system feeds a video wall that is very, very large in the United States. And the total video wall bandwidth that this system feeds is 558 gigabits a second just to that video wall. And all the other bandwidth in the network is just processing that video. So the wall is connected to those 4 switches at the bottom, but all the other switches are doing all the work to make that content happen. If you know the United States and you know where all the really large LED walls are, you can maybe make a guess as to where this is. But I think it's a really cool system. We can also discover all the endpoints inside of it. So you can get a couple different views of this, but Nexus Dashboard automatically discovers all the endpoints connected, and the broadcast controller tells us what they are. Camera 1, camera 2, transcoder X, transcoder Y. We can populate all that information into the topology. And as I said, we can visualize the flows. And I think that this is the coolest feature that Nexus Dashboard has for media fabrics. Being able to visualize exactly how a multicast is traversing across the fabric, across multiple fabrics, across sites, between a WAN. If it's a Nexus, and we manage it with Nexus Dashboard, we can visualize it the whole way. And it's a little anticlimactic with the screenshot, but these lines are actually moving in the direction that the flow is traveling. Bandwidth over time as well. So we support the ability to get flow statistics. So as that flow is traversing across the network and coming in, we'll track its bandwidth over time. If it suddenly drops, the line will drop. Let's say last night you had a black frame of video in the middle of the night, nobody was there, you need to go back. Was it the endpoint or was it the network? You can look here and see if it was the endpoint, or you can look in some other tools to see if it dropped across the network. The purple line is that policer I was talking about. So if we start policing the flow, the purple line goes up and then comes back down as we stop policing it. So here is a system that is deployed as a redundant network. To show you what that looks like, it's 2 independent fabrics, 2 independent network dashboard controllers, or fabrics inside of Nexus Dashboard fabric controller. You can do them in one depending on your scale. There's a single broadcast controller controlling both of these, and the endpoint gets connected to both fabrics. So this is the typical setup of a media production fabric. So as we built all this, we needed to make sure that those operational requirements I showed you at the beginning were met. So this is our response to that. The fabric is completely non-blocking, and we can prevent any bandwidth oversubscription from happening, and we're very low latency, and we support all the speeds possible. It's plug and play. In the broadcast industry, a lot of the people who deploy these systems, the broadcast system integrators, have never seen a switch CLI before. So we needed a system that we could give to somebody who's a CCIE, and they could deploy it, and give to somebody whose only switch experience is with an SG350. Both of those had to be able to deploy the solution. So Nexus Dashboard makes that happen. As I said, security, zero trust, security thought of from day one. Visibility and analytics, because we can't look at video on a cable anymore. Highly available and scalable. We're using spine leaf topologies. We can actually migrate flows across the network as things fail, and we can scale multicast and PTP pretty far, and supporting all those open standards. So that is Cisco's IP Fabric Media, or IPFM for short. Those are the things that it does. All right. How will Silicon One affect the media industry? Well, Silicon One is already part of the IPFM family, so the Nexus 9800 series chassis is what we're actually deploying at a lot of very, very large broadcasters. Obviously, power is a big thing when it comes to Silicon One, so we can be more power efficient, and probably more to come in the future. Right now, we're adding our cloud scale features into that platform to bring it up to par, but as far as bandwidth goes, the possibilities are limitless. We'll finally be able to do 16K in a couple years. That'll be a very large multicast, probably 200 gigs per video flow. Is this broadcast controller deployed as an appliance or on-prem or VM? You propose a clustered topology for HA. So Nexus Dashboard is deployed as a cluster. That's you can buy an appliance or deploy it as an OVA or a QCal file, but it is built as a Kubernetes cluster. The broadcast controller themselves, that's up to them. I mean, that's a piece of software that they manufacture. Some of them have started to support more of a containerized environment. Some of them are still monolithic apps. Some of them support VM, some of them don't. The broadcast industry typically moves in waves of innovation, and sometimes some of those vendors are a little slower than others, but different ones support different things. How do you implement the vendor-specific protocols you mentioned earlier, Dante, NDI, AVB? So specifically to address Dante, they do this really niche thing where they hard code all their multicast packets with a TTL of 1, which is unfortunate. So you have to deploy Dante in little bubbles, and so we do support the ability to do a layer 2 domain inside of the IPFM for Dante workflows and other audio workflows. NDI sometimes has the same problem. They use MDNS for discovery, which is also limited to the layer 2 domain. So you might have to deploy a small little NDI fabric or a small audio fabric inside of the greater fabric to deploy some of those protocols. But that is a bespoke thing per customer. So not everyone uses Dante, not everyone uses NDI, but we do allow all of those to be on the fabric. The only one that the IPFM does not support natively in Nexus would be the AVB, but we do support the importing of Catalyst into an IPFM fabric to support AVB at the edge. Las Vegas Sphere or Times Square screens, the bigger one. Can Nexus Dashboard IPFM multicast visibility flow depict Catalyst 9500 multicast flows? Do you plan on the roadmap to integrate the Catalyst family in the tool? So the Catalyst family is implemented in the tool for configuration and monitoring of the Catalyst itself. Roadmap-wise, we are looking at what we can do in multicast and PTP visibility. How much would the 2-fabric setup cost for a medium-sized broadcast company? Please reach to me after the session, and we'll go through that because that's a longer conversation. I see no references to IPv6. Is only IPv4 used in broadcast? And the unfortunate answer is generally yes. I have not so far seen, except for one broadcast manufacturer that supports IPv6. There's almost no research going into it. So far, all those manufacturers are still just IPv4 based for the uncompressed side of things. Any specific license required for NDFC to display multicast? It's included in your switch license. So Essentials and Advantage or Premier, whichever one you have that feature. Can NDFC Nexus Dashboard be installed in Hyper-V VM? So right now we qualify the appliance, we qualify Linux KVM hypervisor, and we qualify VMware. We are working on looking at other hypervisors as well to qualify. I don't know personally if it does work in Hyper-V because it hasn't been tested by us. All right. There we go. So next we're going to talk about contribution and distribution. And so contribution and distribution is when we hand off content to providers and to transmission. Now, the network can introduce some problems there, namely security. So we have one option that we call remote leaf. If you have a site somewhere far away that's connected over dark fiber, you can deploy a remote leaf there as long as most of the traffic gets sent to the main site. If it all stays internal, maybe that's not the best solution. But some challenges that we might face here is latency on the control side of things, because obviously the control commands from the broadcast devices need to get over there. How will the broadcast controller actually talk to those devices? Do we need dark fiber? Do we need a service provider link? How are we going to do that? And PTP. PTP doesn't work well over WAN, for those of you who might know that. But if it's a dark fiber, we can usually get PTP over there as long as it's synchronous both ways. We also support something called multi-site and PIM border. And multi-site is maybe an oversimplification. This can also be considered multi-system or multi-fabric. So you could deploy many, many sites and interconnect them with a full mesh MSDP, or as I mentioned earlier, PFMSD. And we can use the PIM border feature to interconnect them so that they're separate PIM domains and they don't have interdependency on each other. Typically, we're going to use some kind of border leaf at the edge. But the biggest problem with multicast is there is literally no one paying attention to address ownership. There's no DNS, there's no RIRs, we need multi-tenancy maybe, there's administrative domain overlaps. I've been to so many facilities where even between the same department in one network, they're using the same IP addresses as they are on the other network. It just makes this a whole big problem. So we saw this as something that we could help fix in the interim, and so we created our multicast NAT. So we can ingress any multicast coming into the Nexus switch at line rate directly in the hardware to any other S, G. The important thing here is that because we do it in hardware, we're not just changing headers, it's suitable for broadcast traffic. You can send a 12 gig flow through the Nexus and do a multicast NAT on it, and it will work for broadcast and still be synchronous. We also support that same feature at egress. So we can change the multicast to any other multicast multiple times. So I can take S1G1 and convert it to 2G2, 3G3, 4G4, as many as I want, 40 per interface. The switch supports up to 2,000 translations simultaneously today. And obviously, if I'm doing egress NAT, because I'm doing it in hardware, I need to sacrifice some bandwidth in the backplane. So if you're doing uncompressed 4K NAT translations, you're not going to make it to that 2,000. That's a lot of bandwidth. But if this is your distribution handoff with a bunch of H.264 or MPEG or something like that, one of our customers uses this to just do sub and replaces out towards their providers. So they send a constant multicast stream at a constant source address and can change the input to it based on the NAT over an API. Makes it a lot easier than calling somebody and saying, hey, now you got to subscribe to 239.8.6.5. Much easier. But all that being said, we added something else. Multicast to unicast NAT. So directly in the Nexus 9000 switches in IPFM, or any Nexus 9000 switch that supports the IPFM feature set, you can change any multicast into a unicast. That means that we can send it to public cloud, because the cloud doesn't support multicast, or if you have a WAN, and that WAN doesn't support multicast, you can send it between your sites over the WAN as unicast and convert it back to multicast on the other side. Pretty flexible. It goes both ways, multicast to unicast and unicast to multicast. Here's the other side. All right, a couple more questions. Let's see. Is there anything to watch out for if upgrading from DCNM media? Do I need to do a full redeployment? So you would deploy a new cluster of Nexus Dashboard, and there is a tool inside of the latest releases of DCNM to actually export the config and re-import it into Nexus Dashboard. So we have a tool already built into DCNM for that. You can find me after the session. I can tell you the version numbers for that, so you have them on hand. Is it possible to build a Nexus dashboard controller in cluster between hardware appliance and VM? We don't support the mixing a hardware appliance and a VM at the moment in the same cluster. You either do all virtual or all hardware appliances. You said that before Catalyst 9500 are visible in NDFC, but you cannot see the multicast flow. I didn't understand. This is being looked at for the roadmap. We're planning on trying to do something with the multicast visibility. If you interact with WAN, how do you secure the communication at the edge? So I talked about those host policies. So the host policies also have a subset of features called remote host policies. So you can actually program in policies very specific to other entities reaching into your network. And also, because it's a network switch, all of your other network security tools are actually still available. So if you need to do ACLs or anything like that, you can still do that as well. Is NDFC your only network supervision tools? NDFC is not the only tool, but NDFC is built specifically so that we can have that interaction between broadcast controller in the broadcast world and the network world. So that API and how that all works is a very tightly knit ecosystem. If you want to use other tools at the same time, you can do that as well. I knew this question was going to come up. But we'll get that. Can you ingress and egress NAT the same flow on one box? If you ingress NAT a flow, you can then not egress NAT it on the same box. You would, at the moment, you would need to do a separate box. Will NBM be over VXLAN supported? Yes. So NBM is not supported over VXLAN, at least at the moment. The problem with VXLAN is when you do an overlay with uncompressed media, it doesn't like it. The way that TRM works, for example, if TRM was to do the hashing for the uncompressed flows, you'd oversubscribe something because of the way the tenants work. It's the same for ACI. It's the same on anyone else's VXLAN. You wouldn't put uncompressed media inside of the overlay. Uncompressed media has to stay in the underlay, at least for now. Maybe some technologies will be invented later on for that, but you can run them simultaneously on the same switch. You can have VXLAN running on the switch and NBM running on the switch. They just participate in different FERFs. So that is possible. But we don't put the uncompressed media in the overlay. Alrighty. So coming back to those workflows, what else can we do? Oh, that wasn't supposed to be there. Give me a brief moment. Okay. All right. So we're going to talk about synchronization. It applies to everything. So who here knows what IEEE 1588 is? Still a few no's. A lot of yeses, but quite a few no's. All right. So PTP is a two-way time transfer protocol. And even people who know about PTP don't necessarily know this part, is that it goes both ways. The reference clock, or what we generally call the grandmaster in the network, synchronizes to a follower in the network. It will send a sync message, a follow-up message in two-step mode. The device on the other side gets those two messages. And then it sends something back called a delay request. So that message goes back across the network the other way, and that grandmaster has to reply to it and say, yeah, I got that. This is how much delay you actually have. It sends it back. So it's two-way. The accuracy in a well-designed system needs to be in the nanosecond range and should be in the nanosecond range. And accuracy is not necessarily defined by the switch. Accuracy is defined by the endpoint. Endpoints are in charge of the accuracy of how they clock PTP, but we need to provide a very stable reference to it on the network. There are some devices that do this well and some devices that don't do this very well. But in order to keep this working as efficiently as possible, we need to use something called boundary clocks. Boundary clocks basically make that timing relationship of talking from the master to the follower directly between the port and whatever is connected to it. Because otherwise, PTP is multicast, by the way, it just goes everywhere. Everyone's messages go to everyone because there's no explicit, I'm going to join this very specific source at this multicast, because you never know who the PTP grandmaster is going to be. You join everyone, star comma G, to get all the multicast messages. And so even the ones you don't need, you have to get them and then discard them, and that costs time. This boundary clock gets rid of that by making it a one-to-one relationship. And so, from a diagram perspective, transparent clock and no PTP mode whatsoever is on the right, and boundary clock is on the left. My left and my right, at least. The grandmaster that is in charge is a leader. The boundary clock switch below it is a follower. That's where that timing relationship stops. Now that boundary clock switch is also a leader to the boundary clock switch below it. And that's where that timing relationship stops. And that switch is now a leader to the device connected to it, and that's where that relationship stops, meaning that those messages only stay on that one link. They don't go anywhere else. In transparent clock and non-PTP aware mode, those messages from leader to follower will go to both followers, but the messages from the followers will also go to the other followers. And so in a small network, that's not too bad. I mean, we do this with Dante. But what if you have 10,000 devices? If you have 10,000 devices all talking on a network with no PTP boundary clock, that means 10,000 devices are getting messages they don't need from 10,000 devices at a message rate in SMPTE of 8 messages per second of every message type. That's very logarithmically bad for those devices. The network can handle it. We can push those packets. But these devices have very tiny CPUs generally, especially if they're audio, and they'll suddenly just restart. So that's the problem with PTP and why boundary clocks should be used to have a scalable PTP system. We can provide multiple profiles in the boundary clock as well. So a lot of the concerns I always hear is, well, I need SMPTE PTP here, and I need AES PTP here, maybe some other PTP there. On a per port basis, you can just change what profile you want to send out of the switch. I can have one switch in AES mode, one switch port in SMPTE mode, however you want to do it. So typically when we deploy these systems, for the broadcast guys, I call this a distribution amplifier. We typically build a PTP distribution amplifier because we're going to build more than one fabric. And I want all my fabrics to be timed to each other. And so because I do this, I can have my grandmasters connected at that distribution amplifier, or in the network world, PTP feeder switch, however you want to call it. I'll have them connected to that layer. And then from that layer, I will just send time down to every fabric that I have. In this example, there's only 2 fabrics, a red and a blue. But what if you had 30 fabrics? You don't want to buy 30 pairs of grandmasters all locked to GPS and have possibly a whole bunch of GPS antennas on the roof. You want to just have 2, maybe 4 in some cases, and just have everyone locked to those. And in this case, we can isolate their failure domains as well. So if one fabric goes down, we don't care. If a PTP GM goes down, we don't care. We can do holdover if the GMs go away, or we can just not care about that one fabric on the side if it goes away. PTP will just continue on. If you're a smaller system, maybe a tiny mobile truck or a stadium, you could just connect the grandmasters to leaves and then interconnect the 2 fabrics so that PTP is provided with the same GM ID on both sides. You want that GM ID to be the same on both sides because it makes the failover between red and blue for PTP much faster. For multi-site, especially if it's a WAN, please deploy GPS grandmasters on both sides of the WAN. We do not want to extend PTP over WAN. PTP requires that the link be synchronous both ways and symmetric both ways. On a WAN, you cannot guarantee that the packet will take the same number of seconds to get there as it will to get back. And if that is different, PTP doesn't work properly. We can accommodate for a variation of like static asynchronous delays, but because WANs are constantly changing, you never know what that is, it wouldn't work very well. So deploy a GM at both sides. So you can check PTP on the Nexus switch for those who've worked with it. Show PTP brief, show PTP clock, and show PTP parent will show you basically everything you need to know about the state of PTP on that switch. You can also check the messages per port. You can see the counters interface. So if you want to see how many sync messages it's sending, how many announce it's sending, how many delay requests, responses it's doing, that's available as well. You can also see the corrections that switch is making as it's going through time, because it's doing this correction 8 times per second. It's going to be quite a lot of messages, so you won't see a very large span of time, but you can see enough. But you can monitor an ND and Nexus dashboard. So the drawing on the left, we can actually show you a visual representation of what's called the best master clock algorithm as it stands for that switch. So we can show you, without you having to go into the network and do that show PT parent on every switch, exactly what that election mechanism looks like. And then we also track the mean path delay and the corrections over time. You can see all that right in Nexus dashboard. All right, a few more questions. So I'll address this one now. Is it possible to use a local PTP-GM clock without GPS? And the answer is yes. As long as you have time, that's not a problem. But if you need to send between 2 networks, they need to be the same time. Call it traceable time. So your 2 networks have to be the same time in order for RTP to be able to decode on the other side. So the timestamps have to match. But if you're just one singular fabric and you don't care about sending somewhere else, you can use a local oscillator without GPS. It's done on mobile trucks quite a lot. All right, get back to the new questions. Can NAT chaining affect latency? And if the flow policy is based on multicast address, do we lose the information? So NAT chaining can affect latency in the sense of, I mean, not that much. If you're using our multicast NAT feature, you won't acquire very much latency at all. But yes, you will have to have a policy that also accommodates the new flow address. So if you create a new flow in the switch with multicast NAT, you do need to have a multicast NAT or a multicast flow policy that is associated with that flow. Otherwise, we'll then just deny it the next time it shows up. I didn't see any other questions there. All right. So we're going to address just general visibility into an IP fabric. How do we actually monitor these? I've showed you a little bit with Nexus Dashboard, but let's take that a step farther and see what we can do. And this applies to majority of our workflows. Pretty much everything except that pre-recorded content. How many people have ever had to troubleshoot video across an MPLS circuit? Raise your hand. How many people use the span session to do that? How many people think that sucked? Yeah, it does. Now imagine doing that with uncompressed video and your hard drive's only 500 gigs. 12 gigs a second for 4K, even 3 gigs a second for 1080p, you can't keep that span session going very long before you have to delete the file and start over. And what if you missed that packet drop that you're trying to troubleshoot where it is? Very, very unmanageable. So if that happens, I mean, there's really not much you could do. We had a customer that had this exact situation, and they've been troubleshooting it with their service provider for 3 months. No resolution. Service provider said it was their fault. They said it was the service provider's fault. Not much where you can go when you keep missing capturing the actual packet. So in the Nexus 9000, because of our flow tables feature, we implemented something called RTP flow monitoring. So this is supported on all the top of rack Nexus switches starting in FX, so FX, FX2, GX, and on. We can actually look into the RTP packet without you doing anything. We'll do this automatically, and automatically look for packet drops. We do that by looking at the RTP sequence number. RTP sequence numbers are supposed to go 1, 2, 3, 4, 5, 6. If we suddenly go 1, 2, 8, you dropped packets. We flag this in real time, send the information to Nexus Dashboard, and it's pretty cool. So thankfully, SMPTE 2110 and every other media entity payload that exists, with the exception for one, is based on RTP. So that's what we use to track it. Even if it's unicast, we can still look into that. So now, if I put a Nexus on either side, I can tell that coming out of the event venue, flow's intact, no problem. If I experience packet loss, I'll report packet loss on that first hop into the site. And that tells me that my service provider is dropping packets. Or maybe it's not dropping across that and it's dropping on a leaf somewhere else. then I know it's me. So this feature, you just turn it on when you provision your IP fabric, and then it's running all the time. You don't need to start a span session. You don't need to start the troubleshooting. We will automatically log it for you. This is what it looks like in CLI. So if you configure it, you can configure it very easily by turning on NetFlow and turning on the IPFlow RTP. You'll have to do a reload of the switch when you enable this feature for the first time. But then it will display all the active flows that it can see, and then it will display all the drops. You don't have to look at the CLI. I will get Nexus Dashboard to draw a nice little GUI for you to show you exactly where that packet is dropping. So as long as that Nexus is inside of Nexus Dashboard, I will show you on the topology with that flow the first time it drops, and so on. So if I'm not dropping into the first switch, that switch will just be green. The very first time I see it drop, it highlights it red, and obviously downstream switches also see the drop, so they're red as well. So that's available for you in this as well. And for those that are going to wonder what license this is included in, it's in the Advantage license. As I stated before, everything on the switch is streamed back to Nexus Dashboard, so not just that NBM information, but everything using telemetry, both hardware and software telemetry. So just about anything that happens inside that IP fabric, we can get into Nexus Dashboard, but we also have a very rich ecosystem of third-party entities in the broadcast industry that have integrated with our telemetry as well. So there's very broadcast-specific tools, things like Providius NVRT, and some things from Telestream that just absorb the telemetry natively, and we've worked on integration for them to show that. Check for a few more questions. Can we support PTP v1 and v2 simultaneously? The answer is it depends, as any technical question. So the top of rack Nexus Cloud Scale switches starting at FX support a feature called PTP v1 forward. So normally, when you turn on boundary clock in a switch, it just absorbs anything that's a PTP packet. V1 included and V2, and it obviously discards the V1 because it doesn't care about that because it's a V2 boundary clock. So when you enable PTP v1 forward, it actually looks at that packet and says, oh, this is a V1 packet. I'm just going to forward it on as regular multicast instead of absorbing it into the boundary clock. And so yes, depending on the switches that you're using, that feature is supported. The only one that it's not supported on is the chassis. So you can't use it on the big chassis. But I'm sure you're not doing Dante at 400 gig anyway. Are parts of PTP patented by various switch companies? Well, PTP is an IEEE standard, so everything that's included in the standard is obviously part of the standard, and anyone can implement that. There might be some ways that other vendors and people do specific things with PTP. Some of those might be like FPGA accelerated things like PTP to GPTP translation, stuff like that, but that's not what we do. We just do PTP boundary clock based on the IEEE standard. And do you support PTP v2.1? So PTP v2.1 will currently work if you're turning on boundary clock. We're still a v2 boundary clock, but we actually still look at that field, and because it's a reserved field, the v2.1 will pass through properly. SMPTE is still working on the actual SMPTE 2110 support of PTP v2.1 for the media standard because there's some incompatibilities between the existing media standard and at PTP v2.1 as it exists today. So once SMPTE sorts that out for the SMPTE 2110 standard, we'll probably look at adopting whatever SMPTE puts forward. Okay. So now we need to talk about master control, playout, and graphics. So in terms of IP, master control can benefit from it greatly. A lot of companies are actually doing master control in the cloud these days. One of my customers actually has a very large private cloud that they built specifically for their master control, entirely on IP. Usually what I suggest to most customers is to build a fabric that suits their needs. And so a very small customer, you might have a very small singular master control. So you might just deploy one leaf that just services the master control. But there could exist a case where, like at the TV station I worked at, we have like around 89 master controls, where you kind of want to build an entirely separate fabric just for master control because it's more scalable, reduces that dependency. So this really depends on the scale. Because master control includes storage, we also kind of have to consider that some customers might not want to deploy an entirely separate storage network. So we allow the ability of live workflows and file-based workflows to coexist inside the NBM environment. What this does is basically does a unicast bandwidth reservation. And so normally, when multicast is on the network, multicast always wins in terms of our IPFM solution. If there's unicast there, we will hold it so that the multicast can be prioritized. But what you can do with this feature is basically take a percentage of the link and say, this percentage is dedicated to unicast. Don't let NBM take away that traffic. So this is an optional feature and can be deployed on a link-by-link basis. So the QoS basically makes your storage traffic or any other unicast traffic, maybe it's control, get prioritized by NBM for that percentage of the link. There also exists the case where you could have multi-tenancy in your fabric. Segmentation and security need to be considered. So inside of IPFM and NBM, we support multi-tenancy. You can have multiple NBM instances running on the same fabric in different VRFs. Let's say that you're a service provider and you have part of your fabric being rented out to one company, part of the fabric being rented out to another. They use completely different broadcast controllers. We can support that, no problem. You can have one running in active mode, one running in passive mode, all of them running in any mode, some of them running in no mode. That's perfectly supported by the system. We've qualified up to 16 so far, NBM versus being run simultaneously. A lot of you are going to ask me about ACI probably, if not now, maybe after the session. So for multicast, for those master control workflows, a lot of them are going to be compressed. And as I stated before, in things like TRM and VXLAN, those are overlays. Compressed flows, no problem in overlays. You can do that. A lot of our customers do that. So we do have some customers that will deploy an IPFM for their production traffic, and then they do some kind of transcoding, and then the feeds come into either an ACI or a VXLAN TRM fabric for the contribution and master control distribution kind of workflows. So that is supported, and we can actually provide the end-to-end management and visibility of those as well. VXLAN EVPN is the one most of the broadcast customers have been deploying because it's NXOS and IPFM runs on NXOS. They want to use the same OS for both of them. So we do have a lot of VXLAN EVPN systems working for master control with a side-by-side IPFM for the production side of things. Again, overlays and uncompressed media, no. Overlays and compressed media, no problem. That'll work. All right, going to stop for some more questions here. Do you suggest to use encrypting of the data which flows on the optical WAN lines between different sites? Definitely not a suggestion, but definitely possible. We actually do support MACsec between switches if you want to use that. So we have a customer that actually uses our IPFM solution that's a governmental customer, and their requirement is that every inter-switch piece of traffic be encrypted with MACsec. So we do support MACsec with this feature set, with IPFM, with NBM, and with PTP. So you can do that no problem. So that could be a solution to that instead of just some other type of encryption. Is SMET EVPN type 6 supported, or is TRM the only option? TRM for EVPN VXLAN, I mean, there's other sessions very much dedicated to multicast on VXLAN. I would suggest you go to that session to get some more intricate details on there. But for TRM, that is what we support in the Nexus 9000 today for tenant routed multicast. Okay. So for a conclusion, if we're doing any broadcast workflow, we can do it with IP. There does not really exist a broadcast or media workflow in general that cannot be supported by IP today. There might be individual devices, and we have the means to get those into the fabric. And I don't just mean for regular broadcast. What we're seeing now is many corporations that have things like internal broadcast town hall type systems, they're also moving to IP. All the stadiums are moving to IP because it's just a much more scalable solution and much more forward thinking. And the rate of acceleration in IP is fueled by the IT industry And so there's lots of money always being dumped into IP and into Ethernet to make it better and better as days goes on. There is significantly less investment into things like SDI, into things like XLR cables. I mean, those things haven't changed in a very, very long time, and there's much less investment. So for future-looking technologies, IP has a much larger investment. And so if you can move your workflows to IP, you will benefit from that. Inside of all those IP workflows, some kind of fabric is going to be the glue for a media data center, or multiple fabrics. Using spine leaf distributed architectures makes you much more scalable. Using things like IP fabric for media, using some kind of VXLAN fabric, having a very multicast rich network with very, very large scale. You could have an SDN controller for deterministic and secure media. You really, really, really need that streaming telemetry. How else would you troubleshoot the network? I mean, you could go into CLI, but being able to just pop up a GUI is pretty nice. So again, if you have any questions as you go home, please post them in the WebEx app. I'd be happy to answer any questions about IPFM, or about multicast in general, or about broadcast, or about Canada. If you want to go to Canada, let me know. Please fill out your session surveys. This really helps us. Let us know if the session is good, if you want to hear more, if you want to dive even deeper. Fill out your session surveys and leave that feedback. You can also get a shirt, if you haven't already, if you do 4 surveys. You can also continue your education. There's still some labs and things going on. If you do want a one-on-one meeting with me, you can book it over in the Meet the Engineer. And there's also some other sessions on the on-demand library as well. So thank you.